is going to be what we call limiting reactants. So last week you did your lab where you designed your own little experiment and measurements. I can't unplug that because my iPad took that. Where you were trying to figure out how much carbon dioxide you could make. All right. So I set it up for you where the baking soda decided how much you were going to make of your carbon dioxide. And that's typically what chemists do. One of your reactants is going to run out before the other. When we do our lab tomorrow, you can watch and see which one runs out first. You should be able to tell which one goes away entirely. When you did the lab last week, you should have been able to look in your cup and not see any more baking soda when the reaction was done. All right. So we'll start this with a very simple, not chemistry example, and then I'll show you how to do the math for it. But if you can do a gram to gram, you can do this, I promise. All right. So let's pretend we are manufacturing bikes. Okay. So to make a bike, you need two things. It takes one frame and two wheels, right? And then you can turn that into one bike. That's a one. So let's pretend we're in the bike making business and we're trying to make the most amount of bikes we can, because obviously that's how you're going to make your profit. Sell the most amount of bikes we possibly can. So we go to our warehouse and you walk into your warehouse and you look and you have 10 frames. And we have 30 wheels. Turn to your table. How many bikes are you going to be able to make? Tell your table, some at your table. What part of the bike limited how much you were able to make? What are you going to have extra of left over? The wheels, right? Okay. So in that case, we can go into our warehouse. We could build 10 bikes, right? We will run out of frames. We'll have no more frames. How many wheels are you going to have left over? How many? 10, right? It takes 2 wheels for every bike. We're making 10 bikes. That's going to take us 20 wheels. 30 minus 20 means there's 10 left over. Okay. So another day we go into the warehouse. And again, we have 10 frames because apparently our frames get shipped in groups of 10. But this time now, we have 12 wheels. Tell your friend or friends, how many bikes are we making this time? Here, most of us say 6, right? This time, what limited you? The wheels, right? You're going to run out of wheels. Right? You're going to make your 6 bikes and you're not going to have any wheels left to make any more. How many frames are you going to have left over? 4. All right. This is the same way it's going to kind of work in chemistry. Now we're going to do a real simplified version of the lab you all did last week. But generically, in our little lab, you had your cup, right? Oh, great. We did. And we took some baking soda and some vinegar, baking soda, vinegar. We're going to go real simple notation here. And we mix them together. Okay? They happen to be a 1-to-1 ratio when you balanced your equation last week. And what I did is you measured out your baking soda and you poured it. Most of you, please don't do this today, iPad. You poured it into the bottom of the cup, right? And you measured it. And then I made you overestimate how much vinegar to use. You honestly had about 2.5 times as much vinegar as you actually needed to make the reaction occur. So we're going to equivalently pour in 5 vinegars. So we poured it in. And what happened is this vinegar found the baking soda and turned into the bubbles that got released, right? The carbon dioxide that got released, plus the other 2 products, but they stayed in the cup. And then this vinegar found this baking soda, and again, turned into the carbon dioxide, floated away, and the other products that stayed in the cup. And then do your other vinegars have any more baking soda to find? No, right? So at the end of your reaction last week, if we had analyzed your stuff in your cup, not only would you have the water that you made and the sodium acetate that you made, but there would have been some vinegar left over as well. but you should have been able to look into your cup and not see any more baking soda because it fully reacted. And that's how chemists set things up. Very rarely do you mix like the perfect amounts. You always put one of them in excess. You always make it so one of them has extra and the other gets completely used. Right? And that's what you're gonna do tomorrow. You're gonna do a lab where we do this. And again, I set it up for you. You have to figure out which ones you're limiting in your excess, but I set it up proportionally for you. Okay. So limiting reactant is, and this is a terrible definition, I know, because you're not supposed to use the word in the definition, but it is what it is. So a limiting reactant is the reactant. So it's got to be one of your starting substances that limits the amount of product made. So in your first bike example, it was the frames. The frames were your limiting reactant. They limited how many bikes we were able to make. In our second bike example, the wheels were our limiting reactant. We didn't have enough wheels to make more than 6 bikes. In our lab that we did last week, our baking soda limited how much of the carbon dioxide we were able to make. Your limiting reactant gets completely used up. It's gone. You don't have any more of it. Right. So again, when you looked in your cup last week, there should not have been any more powdery white solid in the cup. It should have all been like stuff in the liquid that was left behind. If you went and made the bikes, again, the first example, there would not be any frames left over. All the frames would have been turned into bikes. In the second example, you wouldn't have any extra wheels laying around. All right. So your limiting reactant decides how much you're going to make, and it's going to get completely used up. Right. Your excess reactant, you will have some left over. All right, you've got extra of it. All right, so there's some of it left over at the end of whatever you are doing. So again, in your first bike example, that was the wheels. There were 10 extra wheels sitting in your warehouse still. In your second bike example, it's the 4 frames that you have left that you can't turn into a bike because you don't have any more of the other ingredient. In your lab, it was the vinegar. All right. And again, tomorrow when we do our lab, you'll be able to tell which one did not get completely used up inside of the reaction, or I hope you'll be able to tell. So your excess reactant, you're going to have some left over, and it's not all of it is used. Now, some of it obviously gets used, right? You have to use some of it to make your product. So you have to use some of the wheels in your first bike, some of the frames in your second bike example, but you're not going to use all of it to do your reaction. So I'm going to walk you through the process because it's not quite as easy as just the wheels and the bikes are to do in your head. If we did it in moles, it would be, but again, in the lab, we don't typically do things in moles, we do them in grams. So it does take a little bit of a process to get to the answer. But if you can do a gram to gram, you can do this. Right? So it says methanol, which is CH3OH, is synthesized by the reaction of hydrogen and carbon monoxide. There's your equation. It's already balanced for you. Right? And this is where it's going to look different. As soon as we start reading this problem, it says if 50 grams of CO and 40 grams of hydrogen, and that's where it's different. Have we had any problems where I'm giving you 2 numbers to start with? No. All right. So here I'm giving you a number for each of them. All right. But our process really not going to be any different. You just get to do extra work. All right. It says what mass of methanol can be formed. So we are still looking for grams of methanol. This is how it's different. Instead of just doing one conversion, guess how many you get to do? 2. All right. So we're going to do one conversion where I start with my 50 grams of CO. And then we're going to do a second conversion where I start with my 40 grams of hydrogen. Okay. We're going to do them both. Okay. It's going to feel long and tedious. Your test will only have one of these problems on it because it does take a little bit of time to write everything down to show your work. But we'll start with the top one. 50 grams of CO. Have to put grams of CO on the bottom. From grams, we go to moles. Where do you find the grams for something? Well, yes, Ms. McLeod, the periodic table. CO is 28.01. And then we'll take our moles of CO and we'll turn them into moles of CH3OH. So remember, this is the one new thing we learned this unit. Honestly, the only real new relationship we learned. Where do you get the numbers to switch the compounds? Equation. This one's nice because they're both ones. And then we'll turn it into grams because it wants grams. So we'll take our mole of methanol and we'll turn it into grams. So we'll do this math. And what this number is going to tell us is if I used up all of my CO, how much product would I make? And it should be 57 grams. Okay. So if we used up all of the CO, we should make 57 grams of the methanol. And then we'll do the exact same thing with our other. All right. So like I said, it's going to feel long and tedious, and I know that, but doing it this way always gets you to the right answer and you're not stopping to logic. There are other ways. If you look them up online, it's fine. It's not like you can't, but most of them are going to require you to write me a written explanation of how you figured it out. Whereas this always gets to it with math. All right. I like the math ways of things. So we'll do this. So we'll take our grams of hydrogen and we'll turn it into moles of hydrogen. And it is H2, so it's 2.02 from the periodic table. And in the middle, we'll make our switch. So we'll take our moles of H2 and we'll turn them into moles of methanol. This time it's a 1:2 ratio. And then your last little fraction will always be the same for the top and the bottom. So you don't have to re-add up the mass. It's the same. So we'll turn this one into methanol. And this one is like 317 point something. If we're being good little chemistry students, sig figs, it's 320. I don't love the numbers that I picked, but so is life. That's the way it goes. Yeah. So you take them both and you convert them both to grams of what you're looking for. Okay. Here's the thing. You're not going to make both amounts, right? You're not going to make 57 grams and you're not going to make 320 grams. You're only going to make one of that. So the question is which one is the right answer? How much am I going to make? All right. So let's go back to our bicycle example and do it like the same kind of logic with that. So what we're doing is we're looking at our reactant and deciding how much we could make with just that number. So if we look at our 10 frames in this first example, 10 frames lets you make 10 bikes, right? Because it's a 1-to-1. Yeah. Our 30 wheels would, in theory, let you make how many bikes? 15. But which one did we pick as our answer? How much did we say we could make? 10, right? In our second example, same logic. Pretend you're using both numbers to figure out how much you can make, as we did with the grams. If I take my 10 frames, I can make 10 bikes. And then the 12 wheels allows me to make how many? 6. And we chose 6, right? So if you convert them both to how much they can possibly make, do we pick the big number or the small number as our final answer? The small one, right? In both of these cases, and I don't know how you logicked it in your head, again, with bikes and wheels, it's not as like complicated, I don't think. You've all done that before, I think, in your mind. But you're converting them both and you pick the smaller answer. You're converting them both to how much they can make and you pick the smaller answer in your head. So guess what we're going to do? When we get to ours in chemistry, we convert them both to product, and which answer are we going to pick? The smaller answer. So this is the answer to the question. Couple of things to point out. If you are somebody who circles all of your answers, please realize you can only circle one. Only one of them is the answer to your question. If you are someone who never circles your answers, on these, you better circle one of them. right? Or at least tell me, be like, this is the right answer. This is how much I'm gonna make, right? Because you're doing two conversions, but only one of them is gonna tell you the most you're gonna make. So in theory, we should make 57 grams. And at that point, all of our CO is gone. We don't have any more of it to react. Second part of it's always going to ask you, who was our limiting reactant? Who was our excess reactant? All you need to do to figure that out, whichever one you circled as your smaller one, go back to the very beginning of that conversion. Here is your limiting reactant. And you can't call the 57 grams of methanol a limiting reactant because that's a product. Okay, so you have to go back to your starting substance, and whichever substance gave that smaller amount, that's your limiting reactant. So what does that mean hydrogen must be? That one's your excess. And so even though, yes, it's kind of tedious, if you convert them both, always circle the smaller answer. And that's the most you were going to make in your like setup that you've got. And you'll do it tomorrow. You'll figure out how much should you make. Because once you're doing your reaction, you should be able to tell which one is your limiting reactant, but you'll do it with math too. So you'll do it visually and you'll do it with math. Now, the last part of it is a little more complicated. All right. So the last thing I'm always going to ask you is how much of the excess is left over? Right? Kind of like with the bikes, I asked you in the first one, how many wheels are left over? And in the second one, I asked you how many frames are left over. Right? Again, with the chemistry ones, it's not quite as easy to do in your head, but it says how many grams of the excess reactant remain when the reaction is complete. Well, we already figured out that hydrogen was our excess reactant. So ultimately, it's asking us how many grams of hydrogen remain. And there are lots of different ways to get to the answer. I can think of 3 off the top of my head. Okay, so there's many, many ways to get there. Logically, it really just kind of depends on you and what you think. All of them involve a subtraction and a conversion. So there's not like one that does less math. They're all going to require that. So what I usually tell students to do, and this is just because I think in terms of like our process, it makes the most sense for like math purposes. Logically, it may not make the most sense, but what most students do is they take these two numbers, okay, and we subtract them. The difference between them is how much more you could have made, right? Like the difference between them, I could have made this much more with my hydrogen. So I do my subtraction first. So I'm going to take my 320 grams of methanol and I'm going to subtract the 57 grams that I know I can make. And I get 263 grams of methanol. And a lot of people would be like, okay, cool, I'm done. Okay, I subtracted, that's the difference. That's how much more I could make, so I'm done. Okay. Here's the problem, is that by subtracting there, that's how much more methanol we could have made, but it doesn't want that. It wants how many grams of hydrogen are left over. All right. So how much more methanol we could have made is going to correlate to how many grams of hydrogen are left over. Well, we spent our entire unit taking one substance and turning it into another. So guess what we're going to do here? Do another conversion and turn it back into the hydrogen. So we'll take how much more we could have made and turn it back into hydrogen. Please don't add up masses. You already have them all. Like everything's already there for you. You just have to show your work. And this is not the only way. So if you've got another way you want to run by me, I will let you know if it'll work. Or if you want to try and find other ways, you can. So we'll turn it back into the hydrogen. Again, like don't re-add up anything. You have all of these numbers already up above. But if we find the difference of how much we could have made more, how much more we could have made, you can figure out how much hydrogen would go with that amount. And it should be 33.2, I think. And that'll tell you how much will remain after your reaction is finished. And again, it's not the only way. So if you started thinking about it and you have another way that you want me to check, let me know, because I'll tell you if it'll work. There are 2 other ways for sure that you can figure out. What am I gonna tell you to do now? All right, make some friends, work together, move around. No, you can't go in the hallway because I can't move well enough to go out there, so we're gonna stay in here today.